Thanks.
I don't know if it is recording.
Yeah. But let's hope it's recording. Okay. We did our masters together in 2001, and I can 100% say that I would never have gotten through that degree without Katy. We like to say it was a collaboration, not collusion. So it's such a pleasure to have you here up at Mount Stromlo, and for you to share the research that you've been doing for the last 3 years, staying on at ICRAR, working with Aaron Ludlow primarily. And so, very excited to hear about intra-halo light as a probe of galaxy assembly. And I'll let you take it away, Katy.
Great. Thank you, Maddie. It's easily the nicest introduction I've ever had. But yes, I'm going to be talking a bit about the work I've done during my PhD, which has been looking at using the intra-halo light as a probe of galaxy assembly, with a predominant focus on cosmological simulations. So yeah, I submitted my thesis last month actually, so it's quite a nice time to present this work. And I realised on the flight over that the first talk I ever gave as part of the PhD was a journal club that Maddie organised as part of Stromlo. So this feels like a nice full circle moment to finish up. Okay, let's get into the science though. So to start with a bit of background, we know that under the lambda cold dark matter model of cosmology, galaxies form in a hierarchical manner. So all of the galaxies we observe at redshift 0, we expect to have some combination of stars that formed through in situ star formation, so stars that form from gas that is cooled and condensed within its own host dark matter halo, and also some contribution from ex situ star formation, so stars that have been accreted from external satellite galaxies that have merged with the central over time. So in addition to affecting the stellar content, we know that mergers can affect the morphology of galaxies, and typically, as you get to higher masses at redshift 0, result in disk-dominated systems transforming into massive spheroids. And you can see that process playing out in a snap from the illustrious simulation there. Okay. So in addition to affecting the stellar content and the central morphology of galaxies, mergers and accretion events can leave a trace in the intra-halo light. So I'm showing an example here at the galactic scale. So it's typically referred to as the stellar halo. And we have some color composite images of the central galaxy in the middle of the images here. And then some deep imaging reveals these low surface brightness tidal features, such as tidal streams and shells, that are results of previous accretion events that may have happened with destroyed galaxies. Cool. And as we move up the mass scale to galaxy groups and galaxy clusters, we have the intragroup and intracluster light. And the formation mechanism of these components are thought to be similar regardless of mass scale. So it's tracing the accretion of massive objects. So I just use intra-halo light as a mass agnostic term for this component in the talk. Okay, so the connection with cosmology and accretion events means that the IHL is kind of this component that's of great theoretical significance, and it provides you with a potential observable window into a galaxy's past. And the most progress or the most detailed observations have happened within our own Milky Way, particularly over the last 10 or 20 years, where we've had astrometric data from Gaia, which has allowed different substructures in dynamical space to be identified, and these can then be tagged to different progenitor galaxies. And you can see an example from a simulation hoping to recreate this, that different progenitors leave different traces in the present day stellar halo structure. And Sven's famous avocado and egg plot is shown here just to demonstrate that you can also complement this with some spectroscopic surveys that give you detailed chemistry on elemental abundances, which can also be used and as a different approach and in combination with dynamics to trace accreted stellar populations too. And these kind of in tandem have revolutionized our understanding of the Milky Way's formation history. Okay, so that's the Milky Way, but as we move to galaxies further afield, things get a bit more difficult. Just by nature, the IHL is a very faint and extended and diffuse component, so characterizing it in galaxies outside of our own is also quite challenging. So this means we're kind of still at a stage where we're still establishing basic relationships. And I've got an example here in this plot. I'm just showing a compilation of this is on the y-axis, the fraction of mass in the IHL relative to the galaxy's stellar mass. as a function of the galaxy's stellar mass. And we can see a few things from this plot. The sample sizes are quite sparse, and there's also quite a large scatter at the scale of the Milky Way mass galaxies. You know, and how much of this is related to physical differences in formation histories, and how much of this may be due to systematic differences between different surveys and different observational techniques is kind of unknown at present. And also how things evolve completely as a function of mass is still being established. Okay, and yeah, quantifying in particular this variability at the Milky Way mass scale is important because it allows us to place what we know about the Milky Way stellar halo in a more broad cosmological context. So that's the current state of IHL observations. Things are quite exciting at the moment. There's a lot of upcoming low surface brightness surveys that are going to revolutionize things, I think. So surveys such as the LSST on the Rubin Observatory and Euclid has recently come online. And that's going to allow us to characterize the IHL over a broad mass range and out to much higher redshifts than we have before. And as an example, the Euclid early release observations have already been used. I think last month a paper was released to infer the progenitors of the ICL using metallicity profiles and intra-cluster globular clusters actually for AVO 2390. And they were able to probe right out to a third of the virial radius. Okay, so I mentioned at the start, my focus is on cosmological simulations, but hopefully that motivates why we're interested in looking at this component. So I'm specifically looking at cosmological hydrodynamical simulations where the baryonic component of galaxies is simulated directly. And these types of simulations have only recently approached a point where at redshift 0, they're reproducing the stellar mass content and sizes and morphologies that are in broad agreement with observed present day galaxies. So as a result, previous studies of the IHL mainly used semi-analytic models where you have to make some assumptions about how the baryons couple to the dark matter. And as such, studies of the IHL usually assumed that it was predominantly or 100% accreted. So there was no in situ component to the IHL in these studies, which observations of the Milky Way suggest that that is not really accurate. There's also been studies using zoom simulations. So these trade sample size basically for resolution. So you end up with a small number of galaxies, but you can perform these detailed studies, and those have typically been focused on Milky Way analogues. So we'd like to broaden the scope a bit to the diverse class of galaxies that form in large volume cosmological simulations. Okay, but a big hurdle that comes with going to large volume simulations is actually defining the intra-halo light. So with some zoom simulations or some other studies, a typical approach, because you have a small sample size of galaxies, you can kind of define it by eye, by making either spherical apertures and choosing an appropriate cut. So I'm showing, as an example here, 3 common definitions. So I mentioned that a fully accreted model is common, so that's what the yellow line shows for Eagle galaxies in a large volume simulation, and then two different aperture cuts. And we can see immediately that all of these definitions produce wildly different predictions for the fraction of mass in the IHL, and they also produce different trends with galaxy stellar mass. And the bottom panel here is just showing the interquartile range, and they also show substantially different scatter at fixed mass. So this discrepancy between previous approaches kind of motivated us to take a more physical approach to defining the IHL. So discuss that as the first part of the talk. Yes, so the rest of the talk is split into 3 different components. As I mentioned, I'll focus on galaxy decomposition, and we use a dynamical technique to split the central stellar component of galaxies, isolate the IHL from the more centrally concentrated components. And then in the second part of the talk, I'll focus on, once we have this definition of the IHL, how does it assemble with time? What's the relative in situ and ex situ contribution? And what can we learn really from the present day component about a galaxy's past? Okay. So first, a brief introduction to the simulations I'm using. So I'm using a combination of 3 different boxes that are all run using the same galaxy formation model, so within the same subgrid physics, essentially. So I'm using the primary box I'm using is the 100 megaparsec reference EGO run. And we supplement this with a 50 megaparsec box that is run using slightly higher dark matter resolution, and that allows us to probe down to lower halo masses and suppress artificial spurious disk heating effects there. And we also supplement with some zoom simulations of 30 clusters that allows us to extend to more massive clusters. So it leaves us with a sample covering about 4 decades in halo mass. Okay, so let's get into defining the IHL. On this plot, I'm showing an example of all the stars that are bound to a halo in the EGO simulation. And the grey points are those that are defined as belonging to the central subhalo, and the orange belong to satellites. So as a first step, we want to remove the satellite galaxies, and then the task is to split the stars that are represented by grey points into disk, bulge, or IHL. Okay, so once the satellites are removed, this plot is showing the remaining stellar particles. And this is the distribution of circularities on the x-axis and binding energies on the y-axis. And we can see for this galaxy, there's an overdensity of points on circular orbits, presumably representing disk stars. And then there's a more tightly bound dispersion component and a loosely bound component, presumably representing the IHL. So to identify these components, we run a multi-component Gaussian mixture model with 12 components. And to then assign those to our physical galaxy components, we make first a cut of 0.5, and any Gaussian with a mean of above 0.5 is assigned to represent the disk. And then we make a relative cut in the binding energies to separate out the tightly bound bulge from the loosely bound intra-halo light. Okay, so the result of this technique is that each stellar particle belonging to a central galaxy is assigned to either the disk, bulge, or IHL using a hard allocation scheme. And we can see this galaxy here is the example we just showed. It results in disks, as you'd expect, are rotationally supported, a compact bulge, and a more extended intra-halo light component. But this also works at higher mass scales where you have galaxies that are better described by 2 components, so spheroidal galaxies where you just have the BCG or the bulge, and the intra-halo light, which itself can be composed of distinct substructure, as you can see in the projection plot there. Right, so we could compare these dynamically defined components that arise from the simulations with component sizes that are derived from observations. And we see that we're in broad agreement. So we're showing separately for disks and bulges where we have observations. We predict sizes that are in quite good agreement with observations, and you can see the disks are slightly offset to higher sizes, but in general evolve as you'd expect as the observations do. And the red line here is just showing the bulge component here. And we see that upturn that observations produce too. And there are no, at present, there's no observed sizes for the IHL. So we make predictions of how that evolves too. You can see that distinct upturn above roughly the knee of the stellar mass function there. Okay, so that looks like we're producing sensible sizes. We can also come back, so this is the plot I showed at the start, looking at the mass fraction in the IHL. So the colored points here are simulated galaxies from EGO. I'm comparing with some observations at the Milky Way mass, and the gray line is just the median trend. So we can see first up that we reproduce the large scatter that is seen at Milky Way masses in observations. And at fixed mass at the Milky Way mass scale, we see that the scatter is clearly linked to the galaxy morphology. So the blue points here represent disk galaxies, and disk galaxies typically have lower fractions of mass in the IHL than spheroids. And this is typically linked to differences in assembly history. So disks evolve quiescently usually, so have lower fractions of mass in the IHL. And as you get galaxies with higher fractions of mass in the IHL, you're tracing more active, messy assembly histories. And then we can see correspondingly the IHL fraction increases with stellar mass, and that as you get to the group in the cluster scale, the IHL fraction starts to level out at roughly 35%. Okay, so I mentioned one of the popular ways to define the IHL, and a more simplistic method is just using a spherical aperture, which is more applicable to observations and you know, as I said, simpler. But we can see that there is a clear, using the dynamical approach, there's a clear difference between, first of all, galaxies of different morphology. So disk galaxies plotted in blue here, we can see that the IHL starts to dominate the mass budget at roughly 30 kiloparsec, independent of halo mass. But for spheroids, the picture is very different. We see quite a strong halo mass dependence on the point where the IHL starts to dominate over the bulge component. And by the time you get to massive groups and clusters, the BCG or the bulge extends out to quite far regions in the halo, and the IHL isn't dominating until about 100 kiloparsecs or more. Okay, so that's kind of saying that the aperture method, you need to be careful, and if you're going to use it, there's kind of a complex dependence on halo mass and morphology that needs to be considered, or that's the prediction from simulations. And lastly, we saw that the accretion model was another common definition, but if we look at what the simulations are predicting for the ex situ fraction in the IHL, if we focus on this left plot here for disk galaxies first, we can see that while the IHL is dominated by ex situ mass, as you'd expect, on average roughly 60% for disks, there's a substantial in situ component, and there's also a substantial scatter in the ex situ fractions of the IHL. So this is common. This has been seen in Zoom simulations, that the ex situ component of the IHL strongly depends on the independent merger histories. And as we move to spheroids, again, we can see that as you move up the mass scale towards groups and clusters, you're getting a larger contribution from ex situ mass. But still, even at the highest masses we're probing, it's never fully dominated by ex situ mass. So we'd like to understand how these different in situ and ex situ components arise for the IHL. Okay, so that covers some of the present day properties of the IHL component. Now we can kind of trace back through time and understand how the IHL assembles. And in this part of the talk, I'm going to do that separately for the in situ and ex situ component. So how do these processes vary with halo mass and morphology, as we've seen, and how does the assembly differ from the ex situ assembly in the disk and bulge component? Okay, so we can see that I'm focusing on now 3 subsets of galaxies. So the top panel showing disk galaxies, roughly Milky Way mass, and then the second spheroid galaxies at the same mass scale. And then we have a sample of cluster mass spheroids. And we can see a few things that we're plotting here, just the contribution of each component in bins, radial bins. And as you get out to further regions in the halo, you see an increasing contribution from ex situ stars. And for disk galaxies at the Milky Way mass, even at the regions we can probe out to in these simulations, while you're dominated by the IHL and ex situ mass, you still see a substantial contribution from disk stars, and you see a component of disks that are accreted, and I'll touch on that at the end of the talk too. And another interesting point shown in these plots is, again, that for spheroids, while you're dominated by ex situ IHL on the outskirts, you do still see a substantial component of IHL that formed in situ within the central galaxy. So we'd like to understand, particularly for the clusters, how you can have an IHL component that forms in the central galaxy, but that is found, out to beyond the virial radius of the halos. We'd like to work out what's going on there. Okay, so people have studied this before, as I mentioned, and there's a few different mechanisms that can produce in situ intra-halo light. So the first scenario, and this is a scenario that's often invoked for the explanation of the Milky Way's in situ stellar halo, is that you have stars that are born in the central region, in the disk or the bulge, and then they're scattered onto halo light orbits during mergers. And this is kind of commonly found in simulations and explains most of the in situ IHL component. The second scenario is that you have star formation that occurs, far from the central regions of galaxies, but that are not obviously associated with any satellite galaxies. So whether this is happening in genuinely isolated molecular clouds, or whether this is happening, as you can see in this image, as a byproduct of interactions, so gas that's been ramp pressure stripped and then isolated star forming regions happening there. That's another scenario that can explain the presence of in situ IHL. Okay, so what's going on with ego galaxies? This plot is showing the in situ, for the in situ IHL at redshift 0, the star formation histories for Milky Way mass galaxies. And I'm splitting this by stars that were born within 10% of the virial radius, which is plotted in blue, and then stars that are born outside of the 10% of the virial radius, to try and distinguish between those two scenarios I just introduced. Okay, so we can see that for the Milky Way mass galaxies, for both disks and spheroids, the dominant mechanism is through stars that are born within 10% of the virial radius. So we can see that for disk galaxies, 61% of the in situ IHL forms in these inner regions. For spheroids, the number is slightly higher, but comparable, 72%. And I don't show this on the plot, but we also find that the difference between the redshift 0 position of the star and where it was born, the in situ IHL typically migrates outwards by 4 kiloparsecs on average, relative to the control in situ sample, which also migrates outwards, but just clearly not as far. So together, these results suggest that the in situ IHL is redistributed by merging satellites. So that's the first example that we saw. And this is true for both Milky Way mass disk galaxies and spheroids. So there seems to be kind of a similar formation mechanism happening there. Okay, but interestingly, as you move up the mass scale towards cluster mass spheroids, we see that trend kind of reverses. So most of the in situ IHL of cluster mass objects is actually born at large radii in the halo. We can see the star formation history peaks around 10 gigayears. So most of the stars were born around redshift 2. So the majority was born in the outer regions, 77%. So how are these stars forming is what we'd like to answer, if possible. Okay, so what drives this in situ star formation? For this example, I'm showing some recently formed in situ IHL, and the points that are color coded by this color bar is the in situ IHL, and then the gray points are a surviving satellite at redshift 0, and the pink points are just clumps of star forming gas that were associated with that satellite. So for this sample of stars, at least, we find that while they were born in the central galaxy, outside at like far regions from the usual regions that are associated with star formation, the particles were previously bound to the satellite as gas particles at the previous snapshot. So either we're having stars that form within the satellite and are rapidly stripped, or the gas is stripped from the satellite and the stars are forming in the tail. And I think the color gradient you see here in this tail of the satellite suggests to me that the gas is being stripped and then the stars are forming. You see the younger stars are actually formed at the base of the tail. So that can explain some of the in situ IHL that's born outside of the central regions. But we find that this doesn't explain the majority. Actually, for 70% of the in situ IHL of clusters, there is no clear association with a satellite. So the satellites are not bringing in the gas, and we can't link these stars to gas that has ever been associated with a satellite. So the origin at present is unclear. I wanted to get to the bottom of this, but my thesis kind of got in the way. And while that was happening, there was an interesting paper that came out looking at finding very similar things actually using the TNG 50 simulations. So using the 3 most massive clusters there, they found widespread in situ IHL with properties that kind of agree with what we found, both in terms of the mass of the in situ IHL and the lack of a connection to satellite galaxies. There was no real explanation provided. I think it's kind of very difficult. They concluded that this would be observationally very difficult to test because of the diffuse nature of the gas. And it's still kind of an open question whether this is some quirk of the star formation recipes that are used in simulations or whether this is genuinely expected to happen physically. So this is kind of an open question at the moment. Okay, so that was the in situ component of the IHL, and we looked at a few different mass scales. We can also look at the accreted component, which is the dominant component of the IHL. So what type of galaxies are responsible for bringing in ex situ IHL stars and disk and bulge stars too? So in this plot, I'm showing the fraction of the present day ex situ mass in each component that has been brought in through destroyed galaxies. So galaxies that have been destroyed in mergers. And we can see that the progenitors of the disk and bulge components, the accreted mass, are usually destroyed by redshift 0. That's because these mergers usually happen earlier in order to get to the central regions, and tidal forces are stronger in the central regions, which leads to the satellite being destroyed. And we can see that the IHL of disk galaxies at Milky Way mass scale is also typically contributed by destroyed galaxies too, but there is a substantial galaxy to galaxy variation in that. And again, we see this strong mass dependence, so that by the time we're at the group and cluster scale, the majority of the IHL is actually brought in by satellites that survive until the present day for these systems. So ongoing interactions with surviving satellites are quite important at the group and cluster scale. Okay, we can also look at the mass function of the progenitors that contribute ex situ mass to these components. So if we focus on the left plot first, I'm showing the progenitor stellar masses of the galaxies that contributed to these components at redshift 0. And on the y-axis, I'm plotting the fraction of the accreted mass that they contributed. So for this galaxy, we can see that there's a satellite of about 10 to the 9.5 solar masses that contributes a significant amount of ex situ mass to both the IHL and the bulge. It is responsible for most of the bulge ex situ mass, and over half of the IHL mass, which is then subsequently built through smaller accretion events. And the plot on the right-hand side is just showing the same thing, but instead I'm showing the stellar mass ratio, so accounting for the stellar mass of the central galaxy as well. And you can think of anything with a mass ratio of above 10% as being minor or a more significant event, where anything below is just a probably smooth accretion. Okay, so to quantify this for the population, this is one example galaxy. We can think of the characteristic mass of the progenitors as those that are responsible for at least 50% of the mass in each component. Okay, so that's what I'm showing in this plot. If we focus on the top row first, we can see a few things. So I'm showing disk galaxies on the left, spheroids on the right. So interestingly, if you look at a fixed halo mass, we see that the types of galaxies that are responsible for contributing to the disk, bulge, and IHL are on average have the same stellar masses. And there's a clear trend with halo mass. But as you move towards looking at the mass ratios of the mergers, we see there's this clear offset again. So disk and bulge, the ex situ mass in the disk and bulge is typically formed through more significant earlier mergers. And the IHL as assembled later. So it's typically the central galaxy is more massive at the time, and it's actually formed through what's closer to a smooth accretion or mini merger event, for disk galaxies at least. We can see for spheroids that the IHL, even at Milky Way masses, is typically contributed by, basically major mergers, close to being a major merger. And there's less difference between the bulge component and the IHL for spheroids. Okay. So that was a lot of information, but just to summarize that part of the talk, we saw that when we split the IHL into the in situ and ex situ component, there are distinct formation mechanisms happening for Milky Way mass halos that are happening to clusters. So for Milky Way mass halos, yeah?
So is it true that you can ignore the stars that get flung out individually by three-body interactions and supermassive black holes? I guess negligible.
Potentially. I don't know if we have the resolution to actually properly resolve that, to be honest.
I assume that they're not in simulations in any sort of way. But in principle, it's a physical mechanism.
It is. I actually don't know whether because they do model black holes, and if they're more massive, you would expect that scattering to happen. And you actually see that happen with dark matter particles artificially because they're more massive than the stellar particles. They start to scatter. That would lead to in situ IHL formation, which would actually be consistent with what we found. What I'm attributing to mergers, I think what you've just said as a physical mechanism could also explain what we're seeing.
It might be negligible in comparison to the processes you were talking about.
Potentially, but yeah, I'd have to look at that, but it's a good point, yeah. Yeah, so that mechanism explains the in situ Milky Way mass formation. And then at clusters, we saw that this in situ component is dominated by stars that are forming on the outskirts. No clear association to satellites. We're not entirely sure if that's real or if it's an artifact of the simulation. More work to be done there. And for the accreted population for Milky Way mass galaxies, we saw that the IHL is built through mostly destroyed, completed merger events with lower mass ratios for disks than you find for spheroids. And for clusters, the IHL formation is dominated by ongoing interactions with satellites with typical mass ratios of 1 to 4, which corresponds to Milky Way mass or low mass group objects, which are building the IHL of clusters. Okay, so I'm just going to finish up by a quick summary of a paper we recently submitted. And it's focusing in on stellar halos, so the Milky Way mass range. And we just wanted to answer the question. I've mentioned at the start of the talk that the variability in the IHL fraction at Milky Way masses is often attributed directly to merger activity. So this is interesting because it provides a potential observable way to constrain assembly histories. So we wanted to see to what extent that actually holds using our definition. Okay, so for our sample of Milky Way mass galaxies, to quantify their merger histories, we're considering the most massive merger a galaxy experienced between redshift 0 and redshift 1, so the past 8 gigayears or so. And on this plot, I'm plotting the mass ratio of that merger separately for disk galaxies and for spheroids. And you can see that while disk galaxies on average are more quiescent than spheroids, disk galaxies experience a range of recent merger histories. So it's been shown that disks can regrow quickly after mergers, provided there's a sufficient gas fraction. So while disks are typically quiescent, not always seems to be the case. And yeah, spheroids on average experience more massive merger events than disks. Okay, so can we use observable properties to infer the mass ratio and the recent merger history? So the mass ratio of the most recent, most massive merger is shown on the x-axis, and on the y-axis of this plot, I'm showing the ex situ fraction. And you can see that, as you'd expect, galaxies that have experienced more massive mergers have larger ex situ fractions by the present day. But this is quite difficult to estimate for galaxies outside of the Milky Way. So we see if the correlation holds for the IHL fraction. And unfortunately, the correlation is much weaker, particularly for disk galaxies, where we can see that while a low fraction of mass, a low fraction of accreted mass at the present day kind of precludes you from having a massive merger event, a low fraction of mass in the IHL at the present day doesn't preclude you from having a massive merger event. So we wanted to try and understand what was driving that difference there. So yes, up to 25%, roughly 1 in 4 of galaxies with low IHL fractions have undergone quite a significant recent merger event. Okay, so we're going to watch a quick video to see an example. This is a galaxy that has a low fraction of mass in the IHL and went through a recent merger. So we're going to see what that looks like. So I'm plotting stars that form within the main galaxy in blue and accreted stars in orange. So if we focus on the right panel first, we're watching the edge-on projection of the galaxy at present day. And we can see that the satellite that merges with the galaxy came in on a fairly low inclination orbit. And it does so in a way that the angular momentum is coherently aligned with the momentum of the disk at redshift 0. Okay. So we saw from that example that the orbit of the merging galaxy may play an important role in where the accreted material ends up. So we can see that while there's 31% of the present day stellar mass is accreted, only a small fraction of that goes to the stellar halo, defined in our dynamical way, and the majority actually goes to the inner bulge or the disk component. So that was one example. You can see how this holds for the population. And to quantify the impact of the merger alignment, I just measure the angle between the angular momentum of the stars in the central galaxy and the orbital angular momentum of the satellite. So cos theta, a value of 1, just represents a coplanar merger event. So we can see for our population, I'm plotting all disks in blue and all spheroids in red, that disks typically experience coplanar mergers at a higher rate than spheroids. And this is known to contribute to the survival of stellar disks during mergers. And we can see that when we further limit the disk population to disks with low mass stellar halos, virtually all of these galaxies underwent a coplanar merger, aside from a few exceptions. So we conclude that, disk galaxies with low IHL, while they usually form quiescently, there are this population of roughly 25% of them that have undergone a coplanar merger that happens in essentially a covert way. And we can check, so you'd expect that while these don't affect the stellar halo, they may affect disk properties. And we find that indeed, as you'd probably expect, this is for all of our galaxies that have low mass IHL. The filled points are those that have active merger histories. And we see that these bound the region of the parameter space where they have higher ex situ fractions than disks with quiescent merger histories. And the disks are also thicker, and I don't show this here, but they are more radially extended than the quiescent population too. So it affects the structure of the disk component itself rather than the stellar halo. Okay. So just to summarize that, we saw that Milky Way mass disk galaxies with low mass stellar halos exhibit diverse merger histories. So while the majority, as has been expected, have quiescent merger histories, there are this population that experience recent coplanar mergers. And this result suggests that there's a limit to the use of stellar halos as an observable tracer of assembly histories, which should be kept in mind for these extragalactic observations that are coming up. Okay, so I'm hoping that was coherent. We kind of speed run the content of my PhD, but I'll just say if anyone is keen to chat about any of this or your research, I'm always keen to hear what people are working on. I'm visiting today and tomorrow, so please come say hello. I'll leave it there, but thanks for your time.
Questions?
Yeah, thank you for the nice talk. I was just wondering, what's the connection between CG and as we concept? It's the idea that the gas, which is like 100 kiloparsec away, forming stars, is that the X C2?
So the ex situ mechanism would be stars that form within satellites, so gas that is bound to satellite galaxies forms within the satellite and then is then tidally stripped as a star.
Okay.
The CGM, I think, is relevant for what we found with clusters. That would potentially lead to in situ intra-halo light. So we find these stars that formed in situ in the main halo at large distances from the central, but how you get like cold dense gas in the CGM, I think is still, people aren't sure how, but if anyone has ideas, yeah.
And maybe the resolution requirement, like what is the difference between resolution close to
so the softening length is 700 parsecs, if that makes sense, and we probe. So we are kind of limited with the Milky Way mass IHL. We've done some resolution tests that suggest like the global IHL fractions are quite well converged given the mass limits we've placed. But in terms of structure, like we don't really resolve streams outside at the far outskirts of the halo, but things are better for the groups and clusters. So that's why I kind of, for the Milky Way mass stuff, we stick to looking at global fractions, but Zoom simulations are kind of needed to look at stellar halos, stellar streams, sorry.
Thank you.
So, as you said at the beginning, galaxy formation is intrinsically hierarchical, a tree with mergers.
Yeah.
Time. And looking at in situ versus ex situ is basically comparing stars that form the main trunk of the tree compared to all the branches that join that trunk over time.
Yeah.
But it's not the only way of slicing the merger tree. You could slice it by the galaxies that all form at a similar time, or galaxies that all form at a similar mass and then join and so on.
Yeah.
And it might be interesting to explore other ways of slicing the merger tree to see how they contribute to the intra-halo light versus the things in the disk involved. Because as you've seen, intra-halo light is not identical with ex situ star formation.
Yeah.
But there might be other slicings of it that give you a better mapping to intra-halo light than in situ versus ex situ.
Yeah, that's a good point. And I think also, as you say, we're kind of simplifying it, looking at ex situ stars, but I think at the cluster scale, pre-processing would also be important. So we see that galaxy groups contribute a lot to clusters, but within galaxy groups, you expect accretion to be important. So, you know, the trees split.
Yeah. Star formation on the tree as opposed to in the galaxy, right?
Yeah.
You'd like to know how stars formed at every stage of that hierarchical merger tree.
And looking at the ages and stuff too. Yeah, definitely.
Do you happen to know whether the IHL is in any way important to absorption of gamma rays that are propagated at cosmological distances?
The honest answer is I have no idea. I'm not sure.
So yeah, it might be something to look at because you're just referring to uncertainties around.
Yeah.
So sufficiently high energy gamma rays will produce on ambient light fields. Okay. So they're in principle sensitive to the energy density of light fields.
Okay.
Along with cosmological distances.
Yeah.
So yeah, if these photons make any contribution.
Yeah, I guess for the groups and clusters, they're a significant fraction. Yes, cool. Yeah.
Really interesting stuff. Question I had is, in the kind of merger scenario, what fraction of the ends up not being so I'm thinking about the context of saying there's things floating around.
Quite low, we find, at least at the Milky Way mass scale, certainly less than 1% of the total stellar mass, but I think higher at the group and cluster scale, but I can't quote you a number. I think certainly less than 5% of the total IHL mass. Yeah.
is there a way, say you let the galaxy kind of relax for a little bit, is there a way to pick apart, you know, the merged galaxy and the original galaxy after 5 billion years kinematically, or would you need to tell which star came?
So kinematically, no, not that I've seen. I looked at a few different things, or at least not what I explored. And even I didn't look at metallicities, but even the ages of the stars, because a lot of the mergers are kind of similar mass objects, and the satellite galaxy typically remains star forming and while it merges, the ages actually aren't that distinct either. So there's not a clear-cut way to distinguish that I've seen, but yeah.
I have a question. Great talk. I was wondering that if the satellite galaxy is not merging with the host galaxy, but just coming very close to it and missing it, is there any possibility of XC2 component in those cases by making the host galaxy disk shake, or very strong ram pressure stripping, just stripping the stars of the satellite galaxy or something? Yeah,
so we found that, I'll show one of the plots if I can find it. Show this plot quick. So this plot was showing the fraction of galaxies, the fraction of the mass and the components that's contributed by galaxies that are destroyed. But the remainder, so if we see for clusters, the majority of the IHL that it's accreted is contributed by satellites that are still survive. So they're still undergoing orbit. So the stars are being stripped, but the satellite kind of survives. It hasn't yet been destroyed. So it's recent accretion. And the IHL is kind of in the process of forming. And those may be responsible as well for knocking out in situ stars, as you were saying.
Do you know if the stripping is by tidal interactions?
I think predominantly tidal interactions, yeah. You find them at kind of far regions as well.
Okay.
Yeah.
Do we have any other questions? In that case, we can thank Katy again. And as a custom, here is Frank Schmidt's wine.
Oh, thank you very much.
Yes. Yes. So Katy will be here for 2 days, today and tomorrow. So feel free to visit her. She'll be in the visitor's office. And we'll also be going for lunch at Beethai after this. So we can all meet out there at 12. Yes. Thank you very much.